All right. Greetings, scholars. Beautiful mind here. I will continue our exploration on Chapter 6, Exponential and Logarithmic Functions. And here we're going to be working on Section 6.2, Graphs of Exponential Functions. A few objectives. We'd like to graph exponential functions and graph exponential functions using transformations. Okay. So characteristics of the graph of the parent function. We have b to the power of x. So recall that the main distinction we have between like a power function versus an exponential function. With the power function, our variable is the base of the exponent. So those are going to be things like x squared, x to the power of 5, 7x to the power of 3, stuff like that, right? But then the distinguishing characteristic of the exponential function is that our variable is in the exponent, is the power. So we're saying we're going to do things like 7 to the power of x, any real number, any positive real number not equal to 1 to the power of x, right? So that's the form, that's a general form of an exponential function. So an exponential with this form, f of x equals b to the power of x, where b is positive and not equal to 1, has these characteristics. It's 1 to 1, so 1 to 1 means that every y corresponds to exactly 1x, which implies that it has an inverse function. Okay, which also means that it passes the horizontal line test, right? So 1 to 1 passes the horizontal line test. Every y corresponding to exactly 1x. All of those mean that the function has an inverse, right? You can find the inverse of the function. Exponential functions have a horizontal asymptote, so without any manipulation, without applying any transformations, in general, the horizontal asymptote is the x-axis where y is equal to 0, right? So the entire x-axis. Exponential functions in general have a domain of all reals, right? So negative infinity to positive infinity. And the range is the open interval from 0 to infinity. So notice that the 0 has a parentheses there, which means that we get infinitesimally close to 0, but our y values never reach 0 without any manipulation. There are no x-intercepts, so it doesn't reach the x-axis. And our y-intercept in general is 0, 1. And again, all of these properties are without doing any manipulation on the exponential function. The exponential function is increasing if our base is larger than 1, and the exponential function is decreasing if our base is less than 1. Okay. Oh, do I have a duplicate slide? It sure looks like I do. Okay, let me get rid of this one. Okay. So on the left here, this is the general form of an exponential function. Some numbers that kind of show you which way it's behaving. Like, for instance, you consider like when x is 0, when x is 1. Sometimes we'll also do when x is negative 1. And that'll give you the general shape of the exponential, those three. When x is negative 1, when x is 0, when x is 1. Same thing here. When x is negative 1, when x is 0, when x is 1. Find the corresponding y, and you'll see that we have exponential decay in this example, right? So that kind of helps. Are we talking about an increasing or decreasing exponential function? So given an exponential of the form f of x equals b to the power of x, how to graph the function? One, we want to create a table of points, plot at least 3 points on the table, including the y-intercept of 0, 1, and then draw a smooth curve through the points, and then state the domain as all reals, and the range is 0 to infinity, and the horizontal asymptote of y equals 0, which is the x-axis. Okay. So here we actually sketch the graph of this, state the domain, range, and the asymptotes. So notice that the base of the exponential is between 0 and 1, so we could, I think, yeah, I guess I'll do it a bit. We can create a table of values, like several values of x. Now let me see. So 0.5 is 1 over 4. Okay. So let's just, we'll do, I'm not going to like go super detailed. I'll do a rough sketch. So like we'll choose several values of x and find the corresponding y. And I'm thinking to choose, okay, I'm going to go -3, -2, -1, 0, 1, 2, 3. So I'm just choosing those x values. I'm going to find the corresponding y values. So when x is -3, that's really going to be 4 to the power of 3. So 16 times 4 is 40. 40 plus 24 is 64, right? So when x is -3, we get a y value of 64. When x is -2, that's going to be 16, and then 4, and then 1, and then I think this one is going to be 1 over 4, 1 over 16, and 1 over 64, right? Okay, so I'm just going to do a rough sketch. So it looks like we have exponential decay. So say this is my positive x in this direction. Say this is my positive y in this direction. Okay. My x's, so we chose, let me see, 1, 2, 3. That's pretty good like that. 1, 2, 3. The y's, I'm not gonna do when x is negative. They're just gonna go off the chart. So we'll go up to like maybe 20. Let me see. 1, 2, 3, 4, 5. Okay, that's fine. Let me see. 7. Threes is kind of weird. We could go by threes. Let me see. 2, 4, 6, 7. I mean, I guess it's okay. So on the y, let me see. So here's the origin. Our x-axis, we went by 1. So this is 1, 2, 3, 4, 2, 3. These are negatives over here. On the y, since I was able to get 7 tick marks, I'm going to go by threes because that'll get me close to 20. Let me think. Yeah, let's just go by threes. So 3, 6, 9, 12. What is that? 15, 18, 21, and so on. And this will be -3 down here, right? So then if we plot these points, when x, now -3 goes off the chart. When x is -2, we're at 16, so that's about here. When x is -1, we're at 4, so that's about here. When x is 0, y is 1, that's about here. And then 2, 1 over 16, so everything else is like really close to the x-axis, right? So then if we connect these with a smooth curve, okay, that's decent. We get something like that. Right? It's a little, I'm not feeling it, but I don't know why it's so weird. All right? Okay, so the domain of this guy. So our domain is going to be all reals, so the very left to the very right. In general, for exponential function, the domain is all reals. Okay. The range, which is the very bottom to the very top, we didn't move it up or down at all, so we can keep 0 to infinity, the open interval. We have a horizontal asymptote, so I should have drawn it. We can do something like this. What I'll do is style about like that and like that, maybe a little bit thicker. Okay. The horizontal axis is the x-axis, which is y equals 0. Okay, I think those are all the parts that this was looking for. Okay, so they chose similar points. Plot the wireness up along with 2 other points we can use when x is -1 and 1. Draw a smooth curve to connect. And that's essentially, we got essentially the same thing. It seems like something is missing because they didn't talk about. I was just looking where they stated plot the wireness up. Draw a smooth curve. Oh, there it is. Okay. So the domain is all reals and the range is 0 to infinity and the horizontal asymptote is y equals 0. Yeah, I was like, where is it? I was like, the question asked for it. That's not like the text to not answer their own questions. Answer the question. Okay, let's keep going. Let me see. Shifts of the parent function of the next exponential function. For any constant c and d, the function f of b to the power of x plus c, and then plus d shifts the parent function of the exponential function. So let me kind of do my own summary before I kind of read through this. So notice this plus c is next to the x. So that's what I would consider an inside manipulation. And inside manipulations cause horizontal changes. Right? These both are rigid transformations. When we add a positive on the inside, it moves our graph to the left that many units. If we subtract a positive on the inside, it moves it to the right. If we add a positive on the outside, it moves it up. If we subtract a positive outside our function, it moves it down. All right. So vertically, let me see. These shift the parent functions vertically d units in the same direction of the sign of d, right? So if again, because we're adding this outside the base function, like somewhere over to the side, outside of the exponential, it's going to shift our function vertically d units in the same direction as the sign of d. And then if we say plus c, it moves it horizontally c units opposite direction of the sign of c, right? So inside manipulations are the opposite of our intuition, and outside manipulations go along with our intuition, right? If we add a positive, it goes up. If we subtract a positive, it goes down. But on the inside, if we add a positive on the inside, even though positive is to the right, this actually moves the graph to the left. Okay? So it tends to be the opposite of our intuition. Let me see. Our y-intercept becomes b to the power of c plus d. Oh, because x is 0, that's fine. They just let x be 0, and that's how they generated that. The horizontal asymptote is going to be y equals d. Yep, because if the d is going to cause it to move up or down, so that's going to affect the horizontal asymptote, and it's just going to match. The range becomes d to infinity, and the domain stays as all rails. So given an exponential with the form f of x equals b to the power of x plus c plus d, how to graph the translation? Draw the horizontal asymptote y equals d. Identify the shifts as negative c comma d. Shift the graph of this c units if c is positive, is left c units if c is positive, and right c units if c is negative. Shift the graph of this up d units if d is positive, and down d units if d is negative. Sorry. State the domain as all reals, and the range is d to infinity, and the horizontal asymptote is y equals d. So let me see. First, they identified the horizontal asymptote. Then it looks like they did their horizontal shift first, and then vertical shifts next. And then, yeah. Okay, let's give that a go. Let's give it a go. So we're asked to graph this guy and state the domain, range, and asymptotes. Okay. So notice that we did move this guy down by 3. Let me see. It does access the graph. So if we think about a general exponential, we went down by 3 and left by 1. Right? Okay. So something like this. Let's see. Okay, so notice again, because of that minus 3, we moved the graph down by 3. So say our 3 is here, or negative 3. So here's our horizontal asymptote. Okay. I think the next one was the y-intercept. So when x is 0, we're going to have 2 to the power of 1 minus 3. So that's going to be 2 minus 3, which is negative 1. Is that right? Yep. Mm-hmm. So negative 1 is our y-intercept. So if that's negative 3, this is the point 0, negative 1 here. Okay. So then, let me see. So we have that +1, right? Now, I mean, honestly, at this point, we could just choose a few values of x and plot the corresponding y. But if we want to list it out in terms of like transformation, this is basically saying that +1 on the inside, remember, inside manipulations are generally the opposite of our intuition. And so that's going to move the graph to the left 1 unit. So we take the original graph, we stretch it vertically by a factor of 2. We move it left by 1 and then down by 3, right? So, for instance, let's choose when x is -2. When x is -2, let me see. We're going to have 2 to the -1. That's going to give us something weird. Not -2, sorry. When x is -1. When x is -1, right, we get 2 to the power of 0, which is 1. 1 minus 3 is -2, right? So when x is -1, y is -2, so that puts us about like here. Let's also do when x is 1. And this was the point, -1, -2. Kind of running out of space a little bit. When x is 1, 4 minus 3 is 1, so then 1, 1. So over 1 up 1 is about here. Okay. And that's enough, all right? And then we just connect them with the smooth curve. Oops. Okay. So then our domain ends up being all reals. So domain is the very left to the very right. Okay. The range is the very bottom to the very top. So the very bottom looks like it's -3. The very top is positive infinity. And our horizontal asymptote is going to be y equals -3. Oops, sorry. Okay, where B is 2 and C is 1. B is 2, right, the base. C is 1, and D is -3. Draw the horizontal asymptote, which is y equals D. So y equals -3. Identify the shifts as -C, D. So this shifts. So the shift is -1, -3. So I guess that just means we're moving it left by 1 and down by 3. That's fine. Shift the graph of this 1 unit, left 1 unit and down 3 units. I've never seen the shift drawn that way, but that's fine. So the domain is all reals, the range is -3 to infinity, and the horizontal asymptote is y equals -3. Yeah, we got the same stuff. Okay. Let's keep going. So given the equation of this form, f of x equals b to the x plus c plus d for x, how to use a graphing calculator to approximate the solution? So press y equals, enter the given exponential equation into the line headed y1 equals, enter the given equation value for this in the line headed y2 equals. Press window, adjust the y-axis so it includes the value entered for y2. Press graph to observe the graph of the exponential function along with the line for the specified value of f of x. To find the value of x, we compute the point of intersection. Press second calculate, select intersect, press enter 3 times. The point of intersection gives the value of x for the indicated value of the function. Let's see if we can see this in action. Solve this guy graphically, round to the nearest 1,000. Okay, so basically what it is, we have two functions, right? What we can do is, this could be the first function, like the first one that we enter, and then we can make this the second function, and the solution is going to be where this horizontal line crosses this guy. So where they intersect is going to be our solution. That's really interesting. I don't know that I've ever done it that way, but it makes sense, right? Let's look at it. Let's see it in action. Close the tabs. We want this guy. All right. Reload and refresh. Let me just get a copy real quick. So we got this 42 equals 1.2 times 5 to the power of x plus 2.8. Okay. Okay. So I'm going to go to my y equals, and I'm going to put 1.2 parentheses 5 to the power of x. That's fine. Then we're going to say plus 2.8. Okay. And then in y2, since it's equal to 42, I'm going to put 42. Okay. Now, a proper window, if y equals 42, I think I'm going to go like 50 in all directions. All right, so I'm going to go window, my x minimum. I think 50 in all directions should be okay. It might look weird, and we can adjust it later as needed. And I'm going to make our tick marks go by 5, so that way we'll have 10 tick marks. The y minimum, again, I want to go negative 50 up to, actually, we don't need to go that far down. So we can make this like, we'll go negative 10, I guess. Y max, we're going to go up to 50, and we're going to go in steps of 5. Let's look at this. Yeah, I knew that was going to be weird. The main thing, I'm just trying to capture where they intersect at the top. So it is behaving like an exponential. It just looks weird because we're so zoomed out. So then what I'm going to do is calculate. So second, I'm going to hit trace so I can access the calculate. And I'm going to hit number 5 because I want to see where do these guys intersect. So then the first curve, right? So I think we're on the first curve. So I'm going to hit enter. And then the second curve is there. And then I want to try to get as close to the point of intersection as possible. So about like there is fine. I'm going to hit enter. So then, so it's saying that it intersects when x is approximately 2.16, we'll say 62. Right? So we're saying that when x is that value, it makes the original true, right? So let's see. And again, this is an approximation. Now, if I want to be more precise, I can write out the long decimal, right? Take it, just write it all the way out. So instead of putting 2, I would have 1943, okay? So then I'm going to verify. I'm going to hit variables. And I just want to make sure that, like, let me quit. Let's try that again. So when I submit that result, 2.1661943, right? We should get a number really close to 42. And we essentially do, right? Because, again, because it's an approximation, that's why it's like a little bit off. But that's okay. We're pretty much there. Okay, so we got this result. Okay. 2.166. We enter the first one, then 42 into the next. It says use the values of negative 3 to 3 for x and 5 to 55 for y, and it hit graph. And the graph should intersect somewhere near when x is 2. For a better approximation, press second calculate and then select intersect. Yeah, so that's exactly what we did. Okay. I'm going to kind of view it with that window because I know we had a different window, so I just want to change the window to their suggestion. So the x minimum was like negative 3 to 3. And we can go in steps of 1 there. The y min, I think they did negative 5 to, I guess, like 50. And I think the 5s are good. Let's hit graph and look at that. Wow, that's interesting. And I've never done it that way. So now we can see it looks more clear like an exponential function, and we captured the point of intersection kind of towards the top. That's interesting. Okay. So stretches and compressions of the parent function of the exponential function. For any factor a positive, the function f of a times b to the power of x, that's going to be stretched vertically by a factor of a if the absolute value of a is larger than 1. It's going to be compressed vertically by a if the absolute value of a is less than 1. It's going to have a y-intercept of 0, comma a. And the horizontal asymptote is going to be y equals 0 with the range from 0 to infinity and the domain of all reals, which are unchanged from the parent function, right? So notice here, we're multiplying the outside of our parent function by some factor of a. So again, when we're doing outside manipulations, that's going to affect our y value, right? The x's should kind of be left alone, and it's going to affect our y values. When we're doing inside manipulation, and by inside I mean like usually it's like pretty much right next to the x. Sometimes it's in parentheses, but it's inside our parent function, right? So for right now, for this part, we're doing outside manipulations. Outside manipulations usually affect the y value, and they follow our intuition. Inside manipulations tend to affect the x value and are typically the reverse of our intuition. Okay. So sketch the graph of this and state the domain, range, and asymptotes. Okay, I think I'm going to try to mimic what we did in the earlier example. So notice here, we're not moving it side to side nor up and down. We're just stretching it vertically by some factor, or we're manipulating it vertically, either stretching or compressing vertically. Now notice that the a is larger than 1, but the base of the exponent is less than 1. So we're going to stretch it vertically by a factor of 4, and it's going to be exponential decay. Okay. So we can choose several values of x. Let me see. When x is -1, -2, -3. Okay. So we'll look at x and f of x. I'm going to start off, I'm going to let x go from -2 to 2. So -2, -1, 0, 1, and 2. So when x is -2, let me think. When x is -2, that's going to be what? 2 squared is 4 times 4. We get a result of 16 there. When x is -1, it looks like we get 8. When x is 0, the corresponding y is 4. When x is 1, we get 2. When x is 2, it looks like we get 1. Okay. Okay. So it looks like we can do a window sort of like this. Again, here's our positive x, our y. Okay. Now our x's just went from -2 to 2. So say this is our origin here. Let me see. We can go, I want my 2 to be about like here. So there's that. And if I mimic that, let me, I'm just being a little bit extra. Let's copy and paste. And then I'm just eyeball it from there. It's about there, right? And again, if I wanted to be precise, I could just open up some like graph paper. And then the y values, so we're just trying to get up to maybe like 16 or 20. I think I'm going to go to 20. Let's see if I paste. Five, 10, 15, 20. I guess that's okay. And then let me see, about like there. So I did this by 5. So here, this went 5, 10, 15, 20. This will be -5, and this is what, 1, 2, 1, 2, and these are negative. Okay. So then let's see. Okay. So when x is -2, the corresponding y is 16. That puts us about here. -1, 8 is about here. 0, 4 is about here. 1, 2 is about here. 2, 1 is about there. The horizontal asymptote is going to be here. Okay. And let's see if I can sketch this curve. So something like that, right? Exponential decay. We didn't move it side to side or up and down at all. Okay, I feel good about this. So then our domain is going to be all reals. The range, 0 to infinity. And a horizontal asymptote, in this case, y = 0. Okay. So before graphing, identify the behavior and key points. Yep. Let me see. So since the base is 1/2, which is between 0 and 1, the left tail of the graph will increase without bound as x decreases, and the right tail will approach the x-axis as x increases. In other words, it's saying we have exponential decay. Since a is 4, the graph of this will be stretched vertically by a factor of 4. So they created a table of points, right? So they chose -3, but that's fine. And then found the corresponding y's and plot the points with our horizontal asymptote. So then the domain is all reals, range is 0 to infinity, and the horizontal asymptote is y = 0. Okay, not too terrible bad. All right. So far we've seen rigid transformations where we're adding a c and a d. The c would cause a horizontal change that was next to the x. Adding d would cause the vertical change, which is outside our base function. We saw multiplying the outside by some number, right? And how that caused a vertical change. So let's see here. With reflections, we're still working with the exponential function, right? With this first part, we multiplied the outside of our parent function by a negative. So that's like our y values are going from positive y to negative y. So it's going to flip vertically over the x-axis, right? So this reflects the parent function over the x-axis. This is, sorry. This is going to have a y-intercept of 0, -1. The range is going to go from -infinity up to 0, the open interval. This has a horizontal asymptote, y = 0, and a domain of all reals. So that's if we multiply the outside by a negative. If we multiply the inside by a negative, again, the inside manipulations typically cause a horizontal change. Usually they're the reverse of our intuition, but here it's going to flip it horizontally over the y-axis. So this reflects the parent function over the y-axis. It has a y-intercept of 0, 1, a horizontal asymptote of y = 0, and the range is 0 to infinity, and the domain is all reals, which are unchanged from the parent function. Okay, so these transformations, it takes getting used to. There is one more. I'll summarize it momentarily. Let's keep going though. We're actually almost done with this section. So find and graph the equation for a function that reflects this over the x-axis. Okay. So if we're going to flip it vertically, that means we need to do an outside manipulation. We want our y values to go from positive to negative. So then our function g is going to take on the form negative parentheses 1/4 to the power of x. So that's going to flip the original function vertically over the x-axis. They want us to graph it, so we got our x versus f of x. Let me see. If it was 3 or negative 3, 16 times 4, 64. I'm gonna start at negative 2. So negative 2, negative 1, 0, 1, and 2. Notice we don't have the plus C or the plus D, so we're not moving it side to side, nor are we moving it up and down. We might flip it vertically or whatever, but we're not shifting it. Okay. So when x is negative 2, that's the same as what, like a negative 4 or 4 squared? Like 4 times 4 is going to be 16 times a negative is going to give us negative 16. Okay. Because remember, our graph should be flipped vertically over the x-axis. When x is negative 1, we get negative 4. When x is 0, it looks like we get negative 1, and then a negative 1 by 4, and then a negative 1 by 16. Okay? So, say this is my positive x. Over here, our y is something like this. That's so crooked. It actually worked. Okay. Is that? I think it's locked into place. Let me check again. Oh, that's the center. Okay, that's good to know. Let's see if we can. Nice. Okay. I like it when it does it, when it like snaps the grid. I didn't even know we could find the center of that segment, but that's good to know. Okay. So our x values, our y values, we want to get down to like negative 20. Okay. Let me see. Let's see if we go. Let's see if we do 2, 4, 6, 8, 10, 12. Oh, so close. 14. Okay. Let me try something else. I'm going to go just a tad bit closer. 2, 4, 6, 8, 10, 12, 14, 16. Okay, we went by 2s there and got it to work. Here we can go by 1, so if that's my 2, that's my 1. And that's comparable. Here's my origin. Let's see, that's 2. So this is 4, 6, 8, 10, 12, 14, 16. These are negative. And this is 4. This is a 1, 2. Negative 1, negative 2. Okay. So then if we plot these points, we have what? Negative 2, negative 16 is here. Negative 1, negative 4 is here. 0, negative 1 is halfway. Oh my goodness. Everything else is really close to the x-axis, but slightly to the bottom. Okay. So then we have a horizontal asymptote. That's good like that. And then our curve. Okay. All right. And then so let's see. Our domain, very left to the very right, is all reals. The range, which is the very bottom to the very top, is negative infinity up to 0, the open interval. And our horizontal asymptote is going to be what? Y equals 0. Okay. Draw a smooth curve to connect the points. We got the same image, and everything else is the same. Okay. All right. So, I think I'll let you. Well, we'll kind of recap this in just a moment. Oof. You have to forgive me. It's like the crack of dawn. Right. I've been up hours. I've been gaming. I was like, well, let me be productive and try to go ahead and do the assignments for next week. Let me think. Okay. So, if I were to summarize transformations, there are a total of 10 transformations, right? The first four transformations are what's called like rigid transformations. These are manipulations that's going to move our graph either side to side or up and down. Right. If we add a positive on the inside of our parent function, that's going to affect the x values, and so it's going to move it side to side. Right. If we add a positive, that's going to move it to the left c units. Right. If we subtract a positive on the inside, it's going to move it to the right c units. If we add a positive on the outside of our parent function, that's going to move it up that many units. If we subtract a positive on the outside, it moves it down. Right? Again, inside manipulations typically cause a horizontal change and are generally the reverse of our intuition. Outside manipulations generally cause a vertical change and they follow our intuition. So we talked about those first four rigid transformations. Then we have the next set are reflections, right? We have two reflections. If we're going to reflect vertically, right, a vertical change, that means we're going to multiply the outside by a negative. If we want to flip it horizontally, then we need to multiply the inside by a negative. So that's 6 of the 10. The last four are stretching and compressing either vertically or horizontally. If we're going to stretch it vertically, we multiply the outside of our parent function by a number larger than 1. If we multiply the outside by a number between 0 and 1, it compresses it vertically. So that follows our intuition. If we multiply the inside by a number larger than 1, that's actually going to cause a horizontal compression, right? Again, that's kind of the reverse of our intuition. We're multiplying by something larger, it causes it to shrink horizontally. If we multiply the inside by a number between 0 and 1, that causes a horizontal stretch by that many factors of that term or whatever. Okay. And this is just another way of kind of articulating what I just kind of said out loud, right? So you can kind of use this as well. Okay. So a translation of an exponential function has this form. I think this captures all but really one. There's still one more that seems like it's missing. But we have this f of x that's taken on the form a times b to the power of x plus c, and then plus d on the outside. Where the parent function is exponential function, where the base is larger than 1. Okay. This is shifted horizontally c units to the left, vertically by a factor. Let me see. Stretched vertically by a factor of the absolute value of a if the absolute value of a is positive. It's compressed vertically by a factor of absolute value of a if the absolute value of a is between 0 and 1. Shifted vertically d units, okay, and reflected about the x-axis when a is strictly less than 0. Okay. Note the order of the shifts, transformations, and reflections follow the order of operations. Okay, so they did, let me see, please excuse, so exponents, and then multiplication. Okay, that's an interesting way to focus on it. So they follow order of operations. So if you think about order of operations, which is PEMDAS, please excuse my dear Aunt Sally's last request. There were no parentheses in this form. So then next would be exponents, which is the plus c. That's going to cause a horizontal shift. Okay. After exponents, please excuse my dear. So any multiplication, which is an a. So then that's our stretching vertically. And then my dear Aunt Sally. So after multiplication and division, then we get into addition and subtraction. So then that's the D. That's an interesting way to articulate it. Okay. I've never seen it articulated that way, but that makes sense. Let's kind of work an example. Okay. I think this might be the last one. So write an equation of the function described and then give the horizontal asymptote of the domain and range. Okay, good. We don't have to graph it. So our base function is f of x equals e to the x. It's stretched vertically by a factor of 2. Okay. So if that's our f, we're going to create a function. We're going to call it, did our pen lose juice? Oh, no. Okay. I didn't even know the battery was low. Ooh. Give me just a moment to try to charge it just to do this example. Let me see. So we're given a function f. We're going to call ours g. All right. Hopefully that's enough to get us to the end. Okay. So here, let me think. So here, let's start with what's given. So the f of x given is going to be e to the power x. Now, first one is we want to stretch it vertically by a factor of 2. So that means we need to multiply the outside of our base function by 2. So we're going to, when I say outside, it's something like this. 2 times f of x, right? Notice that's outside the f of x. That's going to be the same as 2 times e to the x, okay? Reflected over the y-axis so that we want to flip it horizontally. So in order to do that, we multiply the inside by a negative, right? So that's we capture that like, we're going to say 2 times f of negative x, right? So notice the negative is inside the parent function. And that's going to show up here in the form of 2 times e to the power of negative x. I'm going to keep working over here. Okay, and then we shift it up 4 units. So since it's a vertical change, that means we need to be outside of our parent function, so it's going to take on this form. 2 times f of negative x. We want to go up by 4, so we're going to say plus 4. And then that translates to 2e to the negative x plus 4. Right? So then we'll say g of x, our new function, is going to be this guy. Okay. That's fine. I think we're done now. Let me just plug in my pen and do a quick recap. Ooh, here it is. Okay. So we want to find an equation of the general form a times b to the power of x plus c plus d. We use the description to find a, b, c, and d. We're given a parent function e to the x, so the base, so b is equal to e. Okay. The function is stretched by a factor of 2, so then our a is 2. That's fine. The function is reflected about the y-axis, so we replace x with negative x. Did I forget the e? No, I think we got it. Yeah, we're good. Okay. The graph is shifted vertically 4 units, so our d is 4. Okay. Oh, we forgot domain and range. That's fine. 2e to the negative x plus 4. And then the domain is all reals. The range is 4 to infinity. And we have a horizontal axis to y equal 4. Okay. All right. Yeah. So now I kind of like how they did it here, right? Where they had the general form of the exponential of the function. It was f of x equals a times b to the power of x plus c plus d, and then they just identified each component based on the description given. All right, the parent function was e to the x, so the base, sorry, b was e. Like, I like kind of how they did that. I thought it was interesting. If I were to summarize transformations again, there are a total of 10. There are 4 rigid transformations where we move the original graph either left to right or up and down. Then we have 2 reflections where we multiply negative either on the inside or the outside. And then we have 4 distortions, which are going to stretch or compress either vertically or horizontally. Yeah, that's about the best I can do there. Okay. And so with that, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day. Take care. Peace.